Hi there, I'm Mr. Sand, and we're going to talk about vsepr, or valence shell electron pair repulsion theory. You've got a reading on Canvas that looks like this. You go through the reading, and then you go down to the bottom, and it tries to explain everything, and you've got this chart, and it's not full. So today we're going to fill out this chart. The main idea is that an atom can have electron pairs with other atoms. It shares those electron pairs with other atoms. And those pairs will repel other pairs of electrons. So, in other words, the bonds that an atom makes with another atom are repellent to other bonds it makes with other atoms. And I think this will make sense once we get the visual up here. So, if you go through your module, you'll see this molecular shapes simulation, and we're going to go through that right now. So I'm going to go with the model version of this first, and let's see if we can bring up the chart right here too. Yeah. Okay, so I'm going to move this chart off to the side just a little bit, and then this is going to show up too. Great. Sort of. Okay, so the first kind of row, I guess, on this chart is that there are the number of lone pair electrons on a central atom. There's 0. Okay, so what does that mean, a lone pair electron on a central atom? Well, lone pairs are these, they're like what we drew in the little Lewis dot structures. There's those little dots that you have on, I don't know, I'll just show you right here. Let's say that you have H2O. I'll do that very quickly right here. So you've got an O, you've got an H, you've got an H. And for Lewis dots, you would draw these right here. These right here, this thing right here, that is a lone pair, and that is a lone pair. They're a pair of electrons. They're lone pairs. And on the central atom right here, they'd be two lone pairs on the central atom. So it would be something like this, where you'd have 2 right there, or this one. I'm not sure what that one is yet, but we're going to get to it. Here, there's no lone pairs in the central atom, and there's the number of atoms that are bound to the central atom. If there are 2, then it says the electron pair geometry is something we call linear. And the molecular geometry, that's left blank. The bond angle, it says, is 180 degrees, and here's an example, BeH2. So let's go back over to this little simulation. This is going to disappear real quick. Okay, so I'm going to show the bond angles, and you've got the simulation in Canvas, so you can do the same thing. I'm going to show the molecular geometry and the electron geometry. This purple atom right there, that's a central atom, and I'm going to add another atom to it. So it has 2 atoms bound to the central atom. There are no lone pairs. If there were a lone pair, it'd be like that, but there aren't, so I'm going to remove that. There are no lone pairs. The angle between, you can move this around, it's pretty cool. You can see, you can try to make that atom, or the bonded atom, touch the other one, and you can't. They repel each other. They're like magnets. Okay, so this is the idea of valence shell electron repulsion. These bonded electron pairs, right here and right here, repel each other as far away as they can. It's like astronauts in space that hate each other. They're trying to get away from each other, and they're both tied up to this central area. They're trying to get up, they can't. They're repelling each other. So this is 180 degrees. So the molecular geometry, if we look at the shape, that's what molecular geometry means. The shape of this molecule, this whole molecule here, that's straight, so we call that linear. Electron pair geometry, well, that's just telling you the electron pairs here. There's only 2 pairs. There's a pair there, there's a pair there. They're involved with the bonds between these atoms. So that pair and that pair, well, they're in a straight line as well, so they're called linear as well. So we can go back to our chart, thank God, and write in linear. Fantastic. Okay. Now I'm going to attach, so we've got 0 right here. There's 0 lone pair electrons in the central atom. I'm going to say, let's try with 3. I think that's the next one up. With 3 atoms bound to the central atom. And let's see what that looks like. So I'm just going to I'm going to put another one on here. I'm going to stick it on. Boop. And check it out. This is the shape. Pretty cool, huh? This you're looking at it from like above, but if you look on from the side, it looks kind of like that. It's like it's in a straight plane. right? So we call it looks like a triangle. So the molecular geometry here is trigonal planar. That's just a word that you can use. You don't need to memorize this because you'll always have this chart that you're making right now. Trigonal planar, and the electron geometry is the same as well because the electrons are in that shape as well. So it's trigonal planar. So let's write that in our little chart as well. Trigonal planar. Trigonal. Some people say trigonal. Trigonal planar. And the bond angle is 120 degrees. Okay, great. Let's keep this as 1, and let's move this as 3 again. So what's going to happen now? Oh, I don't want to do that. I want to keep that. I'm going to use... I see what I did there. It's going to be 2. Sorry. 2. Okay. So what happens now when you've got one lone pair bound? So let's do one lone pair bound. I'm going to take one of these off, and we're going to have... Oh, there's a lone pair. It looks kind of like a ghost. Some people say it looks like a ghost. You've got one lone pair attached to the central atom. There's the lone pair electrons. Look at that. And it pushes, it squishes those other two atoms out to the side because it repels them, right? But there's no bond there. So this is a case now that we have a slightly different shape from the molecular geometry to the electron geometry. Because the electron geometry, there's 2 electrons there. There's 2 electrons in this bond. There's 2 electrons in that bond. So they're still making that trigonal planar shape that we just saw with 3 bonds. But now for the molecular geometry, so what the molecule looks like, we're talking about the shape of the atoms now. You're just drawing this shape when you go whoosh, whoosh, right there. And that is they have a very scientific name for it. They call it bent. So we need to write that in. Let's do it. So trigonal planar and the molecular geometry is going to be bent. The bond angle is still 120. And example of that is SO2. Right. Now for probably the most common shape that you'll run into for all the molecules. It's where you have 4 bonds to the central atom, and you've got no lone pair. So let's try that. Let's take off that lone pair, and let's put on 4. So we've got 2 right now. There's 3 and 4. You might have thought, well, let me try one more time. So you might think right now, all right, so this is divided into 3. So 360 divided by 3 is 120, right? So if we put another atom on here, well, that'll just change it to 90, 90, 90, 90, right? And you get a different answer because this is adding it in 3 dimensions. You get this kind of shape right here. It's kind of cool. This shape, and look at that, they're all repelling each other. This shape is not 90, 90, 90 between the bonds. It's 109.5. And this is the most efficient, farthest away that these things can be spread out in 3 dimensions. So remember, it's 3 dimensions, not just 2 dimensions. 2 dimensions, it would be 90 degrees. But 3 dimensions now, it's a little bit more difficult. It's 109.5. So we call this tetrahedral. There's 4 sides to this. It's 1, 2, 3, 4. And it's this tetrahedral shape, I guess. So let's fill in our chart. Okay, so the electron pair geometry is the same as our molecular geometry since there are no lone pairs, so that's going to be tetrahedral. Tetrahedral. And the bond angle, 109.5 degrees.